Hi there everybody, welcome to another Chem Complete video, and in today's lecture we are going to continue our study of alkenes and their synthesis by taking a look at the dihalide addition, in which we can take some halogens and create alkyl halides out of them as the result of the synthesis. So that is all coming up on the channel right now. Thank you so much for choosing to learn with Chem Complete today. And remember to head on over to chemcomplete.com for all of your chemistry needs. There's lots of free resources, and it is a great way to support the channel. If you have a few extra bucks, you can buy one of our guides. Now let's get started here. So the dihalide addition for alkenes is going to be a situation in which the addition of Cl2 or Br2 can be added to alkenes and can provide the resulting alkyl halides, and that will give us a 1,2 formation, meaning each carbon involved in the alkene will take on one of the corresponding halides in the resulting product. So what this would look like from a very basic sense is you've got your alkene, which would have its pi bond, and then you are going to expose this alkene to either Cl2 or Br2. So for the example we're going to work with today, I'll go ahead and I'll use Br2. However, I'll mention at the end of this that Cl2 can work almost identically. It has the same mechanism, so don't freak out about that if you've got a problem you're trying to solve with Cl2. Okay, and the result is that you're going to break the pi bond. You're going to add the halogens. So we're going to get one on one of the carbons and one on the other carbon. And then whatever you also had present around the alkene would still remain there. So given our generic example here, we'll just show these wedges and dashes for maintaining whatever else might be there. Okay, so that's the basic premise or synthesis for this. Now, there's something very important in this reaction, which is that the observed halide addition is always anti in its stereochemical outcome. So what that means is that when we deal with the two halogens that have added, they will always add to the opposite side or the opposite face of the double bond. They should never be syn addition or on the same side. And this is important because it means that we will not find a carbocation present during the reaction. So just to walk you through why we wouldn't see that, okay? Let's say that we've got an alkene here, and we'll throw some methyls on here as well. Okay, now if I were to start this reaction and I expose it to the Br2, and we'll take a look at the mechanism in just a minute here. If I were to get to that first intermediate, what I will end up seeing here is that if there was a carbocation, I would expect something like this. And this is kind of what we see during the HBr or HCl addition, where I've added one component. In that case, it would have been the hydrogen. In this case, it would be one of the halogens. And then there would be a carbocation that's left behind on the other carbon involved in the pi bond. Okay, so what we would then expect is that the Br minus could come in, and using one of its pairs, it could attack the carbocation that we have here. Okay, and what we find is that this does not occur. Now, the reason it does not occur, which I just mentioned a minute ago, is that when we observe the product in the lab, it is 100% anti-addition. And if this were the process, this sp2 hybridized planar or flat carbocation would result in a mix of 50% attack from the front, which would then give us 50% syn addition, and it would also result in 50% anti-addition. But because we see 100% anti-addition, we know that this could not be the mechanism. This would not be plausible. Okay, so if you're taking notes or following along, you want to mark down, we know that this does not occur, because carbocations can be common in some of these reactions, but that is not the case here. Okay, so what is the case? What is the actual mechanism of detail that we want to take a look at here? Well, let's go ahead and use the same starting material. So we'll start with our 6-membered ring alkene with the methyl groups. And this time, let's take a look at how that first intermediate forms, because this is going to be important in explaining or looking at the stereochemical outcomes. So I've got Br2, And I'm going to draw this as two separate bromines here. Now, similar to the HBr, the HCl mechanism, you will have a departure of this second halide here. Okay, but what's going to happen is the pi electrons are going to reach out to form a bond with the bromine. But because this bromine has pairs involved in it, it can also reach back out to the alkene and form a bond with it. And so what you end up with is you now have an intermediate that has a three-membered ring with the bromine being at the center of that ring. And there's a technical term that we use for this, and that is called a bromonium ion. So you've got the Br, it would have a positive charge, okay? And then here you would still have your methyl, and you would also have the other methyl down here. So this is the intermediate that we would first come across in this reaction. And again, this is known as a bromonium ion. Okay, and this intermediate is very important in its formation because the sterics are going to prevent the incoming bromine that's left from attacking on the same side as the bromonium ion intermediate. Okay, so when I have the Br, and this Br minus is out here in solution due to the first step where we let go of a bromine, this is going to come in and is going to attack, but it has to attack on the opposite side of the structure relative to where the bromonium ion is. And likewise, this bromonium is going to need to break open. So we're going to have the electrons from one of these bonds, these three-membered ring electrons, that's going to go with the bromine and get rid of that positive charge. So what I end up with is a product where I see that the bromine that came in from behind, because the bromonium was out in front, would be located right here, and that pushed or inverted the methyl to the front as this happened. Okay, and then I have the Br down here that was initially a result of the bromonium ion that formed, and this is the final product that I would observe here. Now, again, this is because when we have the bromine ion, it must attack on the opposite side of the bromonium. Okay, so it must attack opposite the bromonium. And that's the intermediate we saw in the step before this. Okay, so this is really a sterics discussion that we have here. It has to come in the opposite side of that large bromonium. Okay, now, what you also have to realize, and it's not as evident from the product, right, when you look at it, is that when you are doing this mechanism, if you have one side of the bromonium intermediate that is more substituted than the other, meaning you have a tertiary site versus a secondary versus a primary, and so on, the bromine ion is going to attack the more substituted side. And this is important because there's going to be partial positive charge that builds up. You basically are on your way to a carbocation, but you don't actually form one. And that partial positive cation buildup is going to direct the incoming groups selectively to one of the carbons versus the other. So let's just briefly take a look at an example where this is more evident. So what we're going to need is we're going to need to form an alkene, and we can keep it somewhat simple here, but the alkene is going to need to have one side that is more substituted in its alkyl groups versus the other. Okay, so if I put a methyl here, then what I would also want to do is let's just put a hydrogen down here, right? So we can see the left-hand carbon in the alkene is more substituted with alkyl groups than the right carbon is. And following the same mechanistic details, if I expose it to Br2 to begin with, I will get my bromonium. So let's go ahead and draw the bromonium ion that would result here. And as I'm drawing this out, I just want to remind people that this bromonium ion could also form in the dashed or the back position. Okay, it's not guaranteed that it's going to be in this sort of wedged shape. Okay, but by default, that's just how I generally draw most of my examples, is if we're going to have some sort of a three-membered intermediate ring, I like to usually draw them with wedges to stay consistent. Okay, so here's the bromonium ion. And again, this side right here is going to be more substituted due to the methyls, and this side would be less substituted because we have that hydrogen there. So if you remember, what happens here is that the Br- is going to attack. Now, when that bromine gets ready to attack, this bromonium has to break open. So it could either break open from the left, in which case we start forming a partial positive on the carbon on the left, or it could break open from the right, in which case we would have a partial positive building up on the right. And just like carbocations, the more hyperconjugation available, the more stable the intermediate or the process. And so because the bromonium must release some of these electrons as it prepares for the incoming bromine, what we are going to end up with is a partial positive buildup on that carbon. Again, it's not a carbocation because we observe 100% anti-addition, but it is starting to form a carbocation. And so this bromine will come into this carbon that is letting go of those electrons, and you will get your resulting product. Okay, so again, it's not as easy to see if you're just examining the product, and that can be because when you're looking at it, you've added 2 bromines. So it's not very evident as far as like a Markovnikov addition, even though this technically would be, right? Because the bromine of one is really indistinguishable from the bromine of the other when we get to the final product. But if your professor is asking you to show the mechanism and you draw this intermediate here, it is very important which carbon is going to be attacked when we end up with the mechanism. So I just wanted to kind of point this out because some students, they can get the correct technical answer, but if they're being asked to show the mechanism on the test, they do not realize that the bromine needs to come to this more substituted position here. All right, so if we take a look at this, again, bromine here versus bromine here, they are on opposite ends or opposite faces of the molecule. Okay, and then I just wanted to make one last note here before we wrap up, which is the same mechanism for Cl2 is going to be acceptable, but here we are going to have a chlorinium ion that would form, right, instead of a brominium. So what I would have is I would have where the alkene was, I would now have a Cl instead of a Br, and the Cl would have a positive charge. So that's the only main difference that you would see there. The mechanism would be the same. It would still follow the partial positive buildup for the break and everything else like that. Okay, so that pretty much covers the dihalide addition to alkenes. Again, head on over to chemcomplete.com. There's lots of free resources, lab report help, everything else you might need to get through your organic chemistry journeys. And there are lots of affordable $5, $10 options if you would like to support the channel and get a very useful guide, study guide, something that explains a more difficult concept to you like NMR or something like that. So other than that, thank you so much for your support. A like on the video helps keep us boosted in the algorithm. And of course, if you are really wanting to support, subscribing will keep you up to date and it helps to boost the channel. So other than that, that takes care of the dihalide addition. Thank you so much for learning with me today, and I will see everybody in the next lecture.